Welcome back to Minute Science Marvels, where we break down big science concepts in under 15 minutes. Last week, we explored nuclear fission, how atoms split apart to release energy. Today, we're diving into its counterpart, nuclear fusion. If you've ever wondered how stars shine or what the future of clean energy could look like, this episode is for you. So same as last week, we're going to do a deep dive into how fusion works and then look at its real-world impacts, with fun facts sprinkled in all throughout. Let's get started. So, what is nuclear fusion? Fusion is a process where two light atomic nuclei combine to form a heavier nucleus, releasing a tremendous amount of energy. While nuclear fission splits heavy atoms apart, fusion does the opposite. It combines two light ones. The total mass of the new heavier nucleus is slightly less than the combined mass of the original nuclei, so that missing mass is converted into energy, following Einstein's famous equation, E equals mc squared. Fusion happens naturally in stars, including our sun, because of the extreme temperatures in their cores. Temperatures of 15 million degrees Celsius strip the hydrogen atoms of their electrons, creating plasma of free nuclei and electrons. Immense pressure from the gravity forces that hydrogen nuclei, the protons, so close that they overcome their natural repulsion and they collide. A process called quantum tunneling allows this nuclei to fuse, even when they technically shouldn't have enough energy to do so. In the sun, fusion occurs through the proton-proton chain reaction. Hydrogen nuclei collide to form deuterium, which is a heavy isotope of hydrogen, and that releases energy and subatomic particles. Deuterium combines with even more protons to form helium-3, releasing more energy. Two helium-3 nuclei then collide to create helium-4 with leftover protons and energy radiating outward. This reaction is what powers the sun, producing the light and heat that sustain life on Earth. We kind of went over this in the sun podcast, but again, a single photon generated in the sun's core can take up to 170,000 years to reach the surface. After it reaches the surface, it takes 8 more minutes to travel all the way to Earth. So, how does nuclear fusion work? For fusion to happen, atoms need to overcome a major obstacle, their natural repulsion. Protons are all positively charged, and like charges repel each other. So forcing them to collide requires extreme conditions. One of the conditions is high temperature. Fusion needs temperatures of millions of degrees to give nuclei enough energy to smash together. In stars, this heat comes from gravitational compression. On Earth, scientists use powerful lasers or even magnetic fields to superheat plasma. They also need high pressure. Stars like the sun achieve fusion through immense gravitational pressure, squeezing the hydrogen nuclei close enough so that they collide. On Earth, we use devices like tokamaks, which confine plasma with magnetic fields, which mimic the sun's intense conditions. Imagine shaking up a bottle of soda so hard that the bubbles inside are forced to smash together, which creates an explosive release of fizz. In fusion, the bubbles are the hydrogen nuclei, and the explosion is the energy released. Fun fact, a single gram, 1 gram of fusion fuel, just a few drops of hydrogen isotopes, produces as much energy as burning 8 tons of coal. And another really important part of this is quantum tunneling. Even with that extreme heat and pressure, fusion relies on a quantum phenomenon called tunneling. It's as if nuclei borrow energy to sneak through the barrier that would normally keep them repelling apart. This strange but real effect is what makes fusion possible in stars and labs. So why is fusion so powerful? Fusion is one of the most powerful energy sources in the universe because of a pretty simple reason. It converts mass into energy. Like we said before, when two nuclei fuse, the mass of the resulting nucleus is slightly less than the combined mass of the two original nuclei. That missing mass doesn't just disappear. It's converted into energy as described by Einstein's famous equation, E equals mc squared. E is the energy, m is the mass it's lost, and c squared is the speed of light squared because it acts as a multiplier. So why is this more efficient than fission? In fission, energy comes from splitting a heavy atom into smaller pieces, which releases only part of the binding energy that's holding the atoms together. In fusion, the energy comes from forming a stronger bond between two nuclei, which releases a lot more energy per reaction. Think of it like building a campfire. Fission is like burning logs that you already have. It's very effective, but it's limited. Fusion is like discovering a spark that can ignite endless warmth from just a single ember. If we could harness fusion effectively, just 1 gram of fusion fuel could generate the same energy as burning 8 tons of oil without producing harmful emissions or radioactive waste. So why do the sun and stars shine so bright? Fusion is the source of energy radiated by all stars. The constant fusion of hydrogen into helium in their cores releases enough energy to counteract the immense gravitational forces that are trying to collapse them. This delicate balance is why stars shine for billions of years. While fusion does power the stars, replicating it on Earth is a monumental challenge. Here's why. First, the extreme conditions are really hard to recreate. Fusion requires temperatures of tens of millions of degrees Celsius, even hotter than the core of the sun, so we can strip the atoms of their electron and allow the nuclei to collide. It also needs immense pressure to force the nuclei close enough to overcome their natural repulsion. On Earth, we can't rely on gravity like stars do, so we use magnetic confinement, those tokamaks, or inertial confinement, lasers, to try to mimic these extreme conditions. Another issue is containment. The plasma, which is a superheated gas of free nuclei and electron, has to be kept stable and at extremely high temperatures without touching the walls of the reactor, or it'll cool down and that'll stop the reaction. Devices like the tokamaks use powerful magnetic fields to hold the plasma in place, but even tiny instabilities can cause it to escape. Imagine trying to hold a soap bubble without letting it touch anything, including your own hands. If it does, it pops. The whole thing is over. Similarly, the fusion needs to be suspended by magnetic fields because any contact with the reactor walls cools it instantly and stops the whole reaction. Another issue is energy input versus output. Fusion requires a massive amount of energy investment to heat and compress the plasma. Right now, most experiments use more energy to start and sustain the reaction than they actually produce at the end. The goal, obviously, is to reach a net energy gain, where the energy produced is greater than the energy used, a milestone that scientists call ignition. In 2022, scientists at the National Ignition Facility achieved a fusion experiment that produced more energy than it was put in it for the first time, which was a major breakthrough, but it's still far from a practical energy source. Another issue is scaling up for practical use. Even when we do figure out how to achieve fusion consistently, we still need to build the reactors capable of generating large-scale energy at an economically viable cost. But despite all of these challenges, fusion is still worth the effort because it offers a virtually unlimited source of clean energy. There's no long-lived radioactive waste, there's no carbon emissions, and there's abundant fuel. Deuterium can be extracted from water, and tritium can be bred from lithium. Also, for safety, fusion reactors can't really spiral out of control like fission. As soon as the reaction stops, it just stops. The fuel from just 1 liter of seawater could produce just as much energy as burning 300 liters of oil. So it's clean, safe, and nearly limitless. Now to the real-world impact. Fusion isn't just a scientific curiosity. It has the potential to reshape the future of energy and to address some of humanity's biggest challenges. Again, it's a virtually unlimited energy source. Fusion uses deuterium, which can be extracted from seawater, and tritium, which can be bred from lithium. These fuels are abundant and really accessible. Fun fact, the energy produced by fusion is so immense that it could power an entire city with just a few kilograms of fuel. No coal mines, oil rigs, or gas pipelines needed. It's also a clean and safe energy. Unlike fission, fusion produces no long-lived radioactive waste. The byproducts are helium, which is harmless. Fusion reactors are also inherently safe. If something goes wrong, the reaction just stops. There's no risk of a meltdown. Addressing climate change, fusion also doesn't emit carbon dioxide or any other greenhouse gases, which makes it a game changer for fighting global warming. As countries transition away from fossil fuels, fusion could provide a reliable, scalable source of clean energy. And it offers economic and geopolitical benefits. Fusion fuel is widely available and can be sourced domestically, reducing dependence on politically volatile regions. By decentralizing energy production, fusion could empower countries without the traditional energy sources to achieve energy independence. It also has already led to scientific advancements and spin-offs. Fusion research has already led to breakthroughs in materials science, superconductors, and plasma physics, with applications in medicine, industry, and space exploration. The magnetic technology that's already used in fusion reactors is helping to develop cutting-edge medical imaging devices like MRIs. For space exploration, compact fusion reactors could power future spaceships, enabling long-term missions to Mars and even beyond. Fusion's energy density could provide spacecraft with power for propulsion, life support, and exploration tools, potentially revolutionizing how we explore the cosmos. As for the road ahead, while fusion has enormous promise, we're still years, maybe even decades away from seeing it as a practical energy source. Projects like the International Thermonuclear Experimental Reactor are working towards producing sustained fusion energy And recent breakthroughs, like achieving the net energy game, are moving us so much closer. So, to recap, nuclear fusion is the process that powers the stars and could one day power our planet. It works by fusing light atomic nuclei, like hydrogen, to form heavier ones, like helium, releasing massive amounts of energy in the process. In stars, this happens under extreme heat and pressure. On Earth, scientists are trying to recreate those conditions using magnetic fields and lasers. While it's incredibly challenging, fusion has the potential to provide unlimited, clean, and safe energy. Fusion has no long-lived radioactive waste, it emits no carbon, and can't melt down like other energy sources could. It could revolutionize energy on Earth and even power future space exploration. Recent breakthroughs show we're getting a lot closer, but there's still a long way to go. And that's all we have for today. Thank you so much for listening. Don't forget to subscribe, share, download, like, whatever. Also, catch me on other socials. My username is Minute Science Marvels on all of them. I'm on YouTube, Spotify, TikTok, Instagram, and I think I'm going to start on Lemonade. Let me know your thoughts or any questions on nuclear energy in the comments, or even drop some ideas for future episodes. Thank you so much for listening to Minute Science Marvels, and I'll see you next week.